Selamat sejahtera kepada Dr. Muhammad Zamani. So we are from group G1B, and here we are going to present our project for system modeling and simulation BDI 40203, focusing on the torsional dynamic of a wind turbine drivetrain. Drive shafts are almost universally simplified as perfectly rigid link. However, our study highlights a crucial point, where utility-scale wind turbine fundamentally break this assumption of mechanical rigidity. So we identified three primary factors contributing to this significant torsional flexibility. So first, will be the extreme geometry skill. The main drive shafts are incredibly long and heavy, designed to retain the large force, which naturally lead to elastic twisting along their length. So next will be the material elasticity. No engineering materials are infinitely rigid. Under the large torque generated by the large aerodynamic legs, even high-strength steel experience a measurable elastic strain. And last will be the component compliance. The internal component of the gearbox, such as gear carriers and flexible couplings, add an extra layer for structural give to the entire drivetrain. So the key takeaway here are a central premise of our projects is that the drivetrain is not a single rigid rotating mass. Instead of it operating as a continuously highly flexible multiple mass system of wind turbine is rarely calm. So the wind is inherently stochastic, turbulent, and unpredictable. So meaning that the turbine rarely operates under the perfectly steady state conditions. So the most severe challenge comes from the wind gas event, which is characterized by rapid transient rise in wind velocity. So these uncontrolled oscillations will causing two main engineering problem, which is mechanical fatigue. The continuously twisting and untwisting action create a localized alternating shaft stress, so rapidly accelerating microstructural material fatigues and will causing a structural failure. Secondly, will be the grid instability. The transient disturbance cause the generator rotor angular velocity to overshoot its rate limits. Since the electrical output frequency and voltage are directly proportional to the generator speeds, so these mechanical fluctuations will causing as the several vortex flickers and also grid frequency instability. To systematically address this dynamic challenge, so our project follow a clear four-step analytical methodology. So first, we will formulate. So we begin by formulating the dynamic model by using the Newtonian mechanics. So this involves isolating the individual rotating inertia and defining the internal spring and damper force. And next will be the implement. So we will build the computational architectures for our models in MATLAB. So we will utilize a variable step continuous solver to accurately capture the high frequency transient oscillations. And three will be the validate. So with the model implements, our next crucial step is using verification and validations. So this involves the verifying the thermodynamic law consistencies, such as the conservation of energies, and validating our output against the theoretical steady state mathematical limits. And the last step will be the analyze. So we will extract the critical engineering insight by systematically varying key system parameters. So specifically system damping and also the rotation. For our system, we consider of few characters, which is J1 is the turbine rotor, and also the J2 will be the generator rotor. And the shaft will consist of having K torsional stiffness and also the B viscous damper. We can see that the low speed turbine rotor experience an external driving force from the wind, so acting in a positive coordinate direction. So this acceleration is directly opposed by the internal restoring torque of the elastic shaft and also the internal viscous resistance of the damping mediums. So from the left side, we can see that the derived equations. And right side will be another equation where this force pull the lagging generator mass forwards, while the electromagnetic field of the starter applies and opposing a braking load. So the corresponding equation of motion for J2 is on the right. After we derive the two equations using the Newton's equations, so we're using the Laplace transform to transverse the equations into a transfer functions, which is the outputs over inputs. So this is the equations transfer functions that we get.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nurani Najwa binti Salim. So now I will be present about computational architecture and baseline simulation parameters, which is this simulation will set up by MATLAB and Simulink environments utilizing the ODE 45, which is Dorman Prince variable step continuous solver to capture high frequency transient oscillation of a 20-second time horizon. So baseline for parameter matrix, which is first for turbine inertia, 5 multiple 0 power of 6, and generator inertia 5 multiple 0 over 4. 0 power of 4, and torsional stiffness 2 multiply 0 power of 8, and viscous damping 1.5 multiple with 10 power of 6. So that's about the baseline simulation parameter.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Iqbal bin Bakhtiar. My matrix number is ED220029. Today I'm going to present about the verification and validation or VNV. Verification and validation is a process that was carried out to ensure that the simulation model is both mathematically correct and physically realistic. First, let's look at the verification section, which focus on checking whether the mathematical model and numerical implementation are correct. The first verification is conservation of energy. In this test, the damping coefficient B was set to 0. Without damping, the system should continue oscillating forever with no energy loss. As shown in the simulation, the oscillation remained constant and did not decay over time. This confirms that there are no numerical energy losses in the model, so the verification is considered successful. The second verification is equilibrium convergence. As the simulation progresses towards steady state, the difference in angular velocity between the two rotating masses gradually decrease and finally reach 0. This demonstrates that the numerical solution converged correctly to the expected equilibrium condition. Next is the validation process, where the simulation results are compared with theoretical calculation and real-world behavior. For the momentum math validation, the simulated steady state angular velocity was 7.9210 radian per second, while the theoretical value was 7.9208 radian per second. This corresponds to only 0.0025% of error, which indicates an excellent agreement between the simulation and the analytical solution. Finally, for the resonance reality validation, the transient response produced a peak-to-peak frequency of approximately 10.12 Hz. This falls within the expected operating range of 5 to 15 Hz for multi-megawatt horizontal axis wind turbine. This confirms that the model is capable of representing a realistic dynamic behavior. Overall, all four verification and validation tests passed successfully, giving confidence that the simulation model is accurate, reliable, and suitable for analyzing the wind turbine drivetrain system.
Hello everyone, my name is Kelvin Anak Frederick. So today, I will be presenting about the anatomy of a transient wind gust response. So as you can see in this slide, I will start with the wind gust input, where a sudden wind gust applies torque to the low-speed turbine rotor. Because the turbine rotor receives the torque first, it accelerates earlier than the generator rotor. So during the transient phase, the generator rotor lags behind due to its inertia. This because the flexible shaft to twist and store elastic energy. When this energy is released, the generator angular velocity overshoots and starts to oscillate. The peak here represents overshoot, while the repeated up and down motion represents torsional oscillation. The behavior is important because excessive oscillation can increase vibration and fatigue in the drivetrain. After some damping removes the vibration energy from the system, the oscillation becomes smaller until the system reaches steady state, where the angular velocity becomes stable. Hello, and as for the second slide, I will be presenting about the parametric insight 1, which is the critical role of viscous damping. So, as you can see, that this orange curve represents low damping. When damping is low, the system cannot dissipate vibration energy effectively. Because of that, the response has higher overshoot and longer oscillation. And as you can see, this cyan curve, which represents high damping. With higher damping, the vibration dies out faster, the overshoot is reduced, and the system reaches steady state more quickly. So, the key finding here is that damping improves drivetrain stability, which, however, there is an engineering trade-off. Too little damping causes excessive vibration, but too much damping make increased friction and reduce efficiency. So, damping must be selected carefully to balance vibration reduction and drivetrain efficiency. Hi, I'm back with the third slide where I will be presenting about the parametric insight 2, which is the dual nature of rotational inertia J2. So as you can see in this slide, this curve shows that the low inertia condition, when the inertia is low, the drivetrain responds faster because less torque is required to accelerate rotating mass. As you can see for the gray curve, it shows that the higher inertia makes the system more resistant to sudden span changes. So the response is smoother, but it takes longer to reach steady state. The main trade-off is between responsiveness and disturbance resistance. Low inertia gives fast responses, but it is more sensitive to wind disturbance. High inertia gives better resistance, but the system becomes slower. Therefore, inertia must be balanced properly in wind turbine drivetrain design. Hello everyone. As for the fourth slide, I will be presenting about the boundaries of the map, which is the model limitations. This project uses a simplified linear 2 degree of freedom model. The turbine rotor and generator rotor are represented as two connected by shaft stiffness and damping. However, real wind turbine drivetrains experience many nonlinear effects, such as turbulent wind, dynamic friction, and unpredictable load changes. For example, gearbox backlash can cause impact forces and delayed torque transmission. Bearing friction is also not purely linear because it can change with speed, load, and temperature. Real wind turbines also use generator control systems and power electronics, which can affect the mechanical response. These effects are not fully included in our simplified model. So, this model is useful for understanding the basic torsional behavior, but it does not fully represent all real industry conditions. Finally, for the conclusion slide, the MATLAB or Simulink model was successfully developed, simulated, verified, and validated. This project proves that the dual mass torsional drivetrain model can represent the basic transient and steady-state behavior of wind turbine drivetrain. From the results, a sudden wind gust causes overshoot and torsional oscillation in the generator angular velocity. The oscillation happens because energy is exchanged between the turbine rotor, flexible shaft, and generator rotor. The system eventually becomes stable because damping dissipates the vibration energy. The parameter analysis also shows that the damping and inertia are very important in drivetrain design. Higher damping reduces vibration, overshoot, and settling time. Meanwhile, inertia affects the response speed and resistance to disturbance. Therefore, both damping and inertia must be carefully selected to improve drivetrain stability, reduce mechanical fatigue, and maintain stable generator operation. As future improvement, the model can be enhanced by using real wind speed data including gearbox backlash, nonlinear friction, aerodynamic blade torque equations, generator control feedback, and a more detailed multi-mass drivetrain model. That concludes all our presentation. Thank you very much.